So the plan is for the next session, Ted will give some discussion of holography and gravity, and I think tell us about some new ideas, it sounds like, and then the intention is to have an extended discussion following that where we can continue on this set of topics. So, Ted.
Okay, thank you, Steve. And thank you to Steve and the other organizers for this very stimulating and useful meeting. Steve tasked me with talking about holography and gravity, which I just freely reinterpreted partially as talking about the relation between holography, gravity, and the information paradox, and also to give me an opportunity to talk about what I think is the solution to the information paradox, the correct formulation and solution. So I just want to be quite informal and basically make a list of points, try to stay disciplined so I don't waste time, because Steve's idea was that this 90 minutes would be about half me summarizing some points and half us all discussing things. So, questions that might lead us into long discussions you should probably save for afterwards. So the first point is that the key thing about gravity is diffeomorphism invariance that we have to learn how to grapple with, and that leads to the issue of observables, so non-locality of observables, all observables, non-factorizability of Hilbert space, and the problem of time, I guess, might as well throw in there, time evolution, or time, and so forth. And basically, to get off the ground, the greatest thing since Swiss cheese in quantum gravity was to adopt a time-like boundary to space-time, so we could anchor a lot of discussion there and still be discussing the physics of a diffeomorphism invariant theory. So I want to do my whole discussion in the context of asymptotically ADS space-time. So use asymptotic ADS, which has its time-like boundary, to anchor observables and to have a common notion of the flow of time, to basically simplify our problem. Not that we'll simplify, not that we'd ultimately be satisfied with this, but if we could really solve the whole thing in this context, well, it seems quite likely that we would have figured out a lot, and then we'd be prepared to take the next step, as I think Sean mentioned in his talk yesterday, and sort of address what we'd really like to, which is physics which isn't necessarily anchored at a time-like boundary. But I'm going to just use asymptotic ADS. Now, it's interesting that once you do that, and you have diffinvariant theory of gravity, basically you have holography and ADS CFT. So even though ADS CFT came originally from string theory, once we've discovered it, it's basically what you get if you do quantum gravity in asymptotically ADS spacetime. There's a quote I like from Witten's 1998 paper called like anti-de Sitter space and holography, where he said any ADS theory, well, I'm going to leave out the dots to specify what kind of a theory, but we're talking about diffeomorphism invariant theory that includes gravity, appears to give boundary correlators, boundary correlation functions that obey the general axioms of conformal field theory. So, and that means, like, you know, besides the operators having conformal scaling dimensions, etc. But it's important also that the boundary notion of causality is imprinted on these correlators so that they, you have commutation at space-like separation with respect to the boundary conformal metric. And so basically we could say that if we're doing quantum gravity in this setting, we're doing ADS-CFT. But actually there's a huge step up in this procedure, because once we say that, then we could be talking about a CFT, which is a UV-complete theory, whereas the theory we started with here, I didn't list it, but aside from diff invariance, a huge issue is that general relativity is not a UV-complete theory. So one completion is, or maybe string theory, but in this kind of way of looking at it, once we could figure out some conformal field theory that matches onto the classical or semi-classical limit of general relativity, that conformal field theory is then a candidate UV completion of the quantum gravity theory in the bulk. So it's just a very powerful transformation of the problem into something much more manageable. Okay, so then what do we get among these boundary correlators? We have the stress tensor of the conformal field theory. So some boundary operators that are key would be the stress tensor. And from the stress tensor, we could make, in particular, the Hamiltonian by integrating over a slice of the boundary, the stress tensor, the killing field that generates the time translation that we're trying to construct the generator of. And so we have that Hamiltonian too. And so key then is that we've got this Hamiltonian, and it's the Hamiltonian of the gravity theory in the bulk, even though it's only a boundary term. Now, how can that be? Well, that's because that's the way general relativity works, because of diffeomorphism invariance. That the, let's see, what order did I want to say this in? So I'm in the context of Dirac constrained quantization, we would say that the full Hamiltonian, well, actually, even before we say constrained, the full Hamiltonian of general relativity could be written as an integral over a space-like slice of our asymptotically ADS manifold times constraints, with the Lagrange multipliers being the lapse and shift, and then some boundary term. Let's call it H del. We could reduce the theory completely at this stage instead of, so one point of view, and the one that I'll focus on and that we seem to usually focus on, is where we think about states being annihilated by these constraints and observables commuting with these constrained operators. And that's a kind of Dirac quantization. And for those observables, they time evolve just by this piece in the Hamiltonian, the boundary piece, because they commute with the bulk piece. It's always bothered me a little bit that we could, well, hey, what if we just decided to reduce the phase space right at the beginning of this discussion down to gauge fixed, gauge invariant description? And that's a different way to approach quantizing the theory. And I just wanted to advertise that there's an interesting 1982 paper by Ashtekar and Horowitz, actually comparing Dirac quantization to reduced phase space quantization of general relativity, in which they make an interesting point that people might not have thought of, which is that if you reduce the phase space, then because we know that, you do that at the classical level and then quantize. Classically, we have the positive energy theorem. So the phase space doesn't include metrics, spatial metrics, which have a negative ADM mass. Whereas if you just do the Dirac quantization, then the wave function starts out as a function of 3 metrics, or d-1 metrics, which satisfy the constraints, and those metrics don't have to have a positive ADM mass. And they have to satisfy the constraints, but the constraints are not going to rule out the argument having a negative ADM mass. So they really look different, and they spend some time in the paper looking at a toy model, trying to get some insight into whether these could really be equivalent, and if not, which one should be considered the right one. Yeah.
So advertise my talk tomorrow that I'm actually getting a prescription of relating Dirac to reduced quantization.
Do you claim they're identical?
No, but I mean.
Oh, okay. Yeah, so they advocated in the paper actually that they're not identical, and in fact that if the one that's more correct would be the Dirac one. I'm not sure I actually agree with their arguments, but that's kind of irrelevant for today, because for today I'm just going to adopt this Dirac quantization viewpoint and not think beyond this point about reduced, although I think it's an important point. Okay, so then in the Dirac quantization, observables should evolve by h. And so let me just write down that evolution equation. Let's see, this is the front. Whoop. So it goes like, I think an infinite number of derivatives vanish when it starts going, don't you? Okay, so the next point is an argument by Don Marolf for what he called boundary unitarity that follows from what I just said already. So let me just... So the idea is that observables O should commute with the constraints C mu. Did I write it up or down? This is gauge invariant observable. Okay, observable by definition is observable, so it's gauge invariant. And this implies that the equation of motion, I times the time derivative of the observable, is the commutator of the observable with the Hamiltonian, but it commutes with the part of the Hamiltonian that's a bulk term, so this just becomes the commutator with the boundary. So that's not Don's observation. But what his observation is suppose I restrict attention to observables that live at the boundary. So we'll call those boundary observables. I should define really what I mean by that. So let's say I pick a Cauchy slice of the bulk spacetime and then take some arbitrarily small neighborhood of where that Cauchy slice intersects the boundary. It goes all the way around, but it's a smaller than any finite size region. Consider any observable that you can construct from the values of fields in such a limiting region at the boundary and call that the algebra of boundary observables. I'll give it a name, A sub del. This is the algebra of boundary observables. So if you have something in that algebra, well, like every other observable, it evolves by this equation. Now, Don's point is that among the observables in that algebra is this boundary Hamiltonian itself, because it's just like the ADM Hamiltonian for gravity, well, plus whatever we have to add to the general relativity to UV complete the theory, and I'll come back to that later as a possible flaw in this argument. But for now, it's a boundary integral, and so it's in the boundary, and it's an observable, so it's in the algebra of observables. So the time derivative of this observable is just a commutator of two other observables in the same subalgebra, namely the boundary algebra. So
how do you know that this is necessarily an algebra, that these operators form an algebra?
I can multiply them? What do you mean by how do I know?
Well, so where are these operators? Sorry, can you just define one more time what these operators, these boundary operators are?
All operators you can so the way we're working here is in this Dirac quantization picture. So we start with like a kinematical Hilbert space. The fields are like, say, the 3-metric and 4-dimensional space-time and maybe other fields. Their values at the boundary, meaning in any arbitrarily small neighborhood of the boundary of a Cauchy slice, are fair game for constructing these boundary observables. But I want to construct ones that ultimately that will commute with the constraints. So I'm not going to write like, G mu nu at some point in coordinate system. I have to construct where it is, like in Pfefferman-Graham coordinates or something of specific gauge.
This answers my question.
Yeah, so the key point now is that the time derivative of our boundary observable then is another element of the algebra of boundary observables. So that algebra seems to just evolve into itself under time. And it evolves unitarily if the Hamiltonian is a Hermitian operator in this algebra, which I'm not going to question at this point. It starts out as a real thing in the classical theory. Presumably I managed to quantize this, preserving that, or else I failed in the first step. So this implies that A del evolves unitarily into itself. And Don named this boundary unitarity. Which I'll abbreviate by BU. Okay. Now this boundary unitarity is quite surprising because it says that no matter what you throw into the bulk from the boundary, or no matter what reaches you at the boundary from inside the bulk, you never gain or lose any information because the set of all observables at your disposal is evolving unitarily. So how can that be? That actually raises a paradox. One version of it is the black hole information paradox. Suppose I throw in from the boundary something that forms a black hole. The black hole starts radiating Hawking radiation. The radiation comes out and reaches the boundary. It looks like the Hawking effect has the property that a Hawking quantum is entangled supposedly with something inside the black hole. And so the Hawking quantum by itself is not even in a pure state, and yet it's reaching the boundary and mixing it up with boundary observables here where it can be detected. So it seems impossible that the boundary algebra of observables could evolve unitarily into itself. Notice, though, that argument really, I didn't need a black hole to get confused by this or to create a paradox. Actually, almost anything that happens in the bulk will lead to a paradoxical situation. And therefore, in the paper that Fuchs and I are hopefully just about to put out, I should say this is a very well-aged paper. I wrote on this topic in 2012 and haven't written a word about it in public since then. And we've been working on it together for about a year. And I think we're just about to come out with a paper on this very, very soon. And we called it the boundary information paradox to distinguish it from the black hole information paradox just because it's a more generic thing and doesn't require black holes. And so just to have a concrete example of it in mind, you could imagine that we throw stuff in from the boundary and then we make a state which is not a black hole but is a long-lived resonance. And it might emit some radiation initially, but then have a very long lifetime, and then finally decay completely. And if this is a pure state to begin with, yes?
I don't know if you want to finish, but if I were just from the boundary point of view, I just had like some field theory in Minkowski's space, would this statement be surprising? It seems unsurprising to me that the algebra of observables at one time evolves into itself.
Right. No, I mean, that's exact. It's completely obvious.
So
the problem.
Statement of the fact that the boundary theory is unitary.
Right.
Okay. So
But what's puzzling is that, so I could send in a pure state, a pulse of energy, create this resonance, and let's just consider this idealized situation where it first emits a prompt gamma ray, and then it emits a later one. But this is in a mixed state, and it's entangled with the resonance that's left behind. It's not a black hole, it's just some resonant state. And so within the bulk description, I would have said that by itself, this thing is in a mixed state, and it's entangled with that. And it's only after that reaches the boundary that I would sort of recover, it looks like, a pure state in the boundary. Because this could come tickle my boundary observables, but it's entangled with something that's still deep inside the bulk. So I'm claiming that this is directly analogous to, and in fact I would say essentially equivalent to, the black hole information paradox. Now, usually people talk about that paradox kind of thinking of the initial state being pure and then asking whether the final state is pure. But because boundary unitarity says more than that the S matrix is unitary, it says that the time evolution of the boundary state is unitary. So on every slice of the boundary, I must have a pure state, or in terms of the algebra must be unitarily related at this time to whatever it was at any earlier time. In particular, long before we get to this point on the boundary, it looks like, let's say when I'm here, the resonance is still deep in the bulk, and this boundary degree of freedom is somehow entangled with this. So how could this possibly have evolved unitarily from here?
The existence of the resonance is still encoded in the boundary state.
Of course, yeah, this is what we need to understand. And that's all we need to understand in the black hole information paradox. Actually, I'm about to make a caveat because Raphael is there and he raised his hand. We have to discuss the Busou paradox. The Busou paradox is the infaller paradox, which is quite different from this statement. The infaller paradox, as Raphael actually summarized, I think, yesterday, or maybe what?
The first day.
The first, okay, is this idea that Alice could fall into a space-time of an evaporating black hole that's more than half its evaporated, distill out from the early Hawking quantum a special qubit which has the special property that it's maximally entangled with the next Hawking quantum that comes out, and she knows where it's going to come out. I'm going to critique this argument later, but just to state it really quickly, she can possess this special qubit that's maximally entangled with the next Hawking quantum. On the other hand, the next Hawking quantum has to be maximally entangled with its partner behind the horizon. And then she faces a real problem because just in a context where local quantum field theory should apply, she has a contradiction because of the monogamy of entanglement or a strong subadditivity of entanglement. It's impossible that she could possess this qubit that's maximally entangled if at the same time the Hawking quantum is maximally entangled with its partner, and therefore certain people create the abomination of a firewall to prevent this Hawking quantum from having a partner to be entangled with, somehow though they still have the Hawking radiation. But let me postpone till later. I just want to make the point that this paradox, the infaller paradox, involves statements about what Alice is doing inside the bulk and what she's able to do, and those are quite different in character. And my philosophy about the problem is that if we can first resolve with a clear head the boundary information paradox, we'll be far along the path of being able to understand how we should think about the infaller paradox. But I am totally putting it aside until later in the talk.
My question is not about the firewall story. I mean, it's just, if we get to peek at the answer here, we have completely resolved this paradox. Right? So it's just, you can't express the information about what's deep inside the space-time in terms of local operators at one time. You have to use operators that are either highly non-local or spread over. So, but we can peek at the answer in ADCC. We know exactly how to do it.
Exactly, and I'm going to elaborate on that and why it's.
How to do it for zeroth order, we have no idea how to do it for black holes. So I think from that perspective, it's really two very different problems. I don't think this is a good model for the firewall problem.
Can you explain what the paradox is? How is this situation different from the collisions that we have here that are detected on the boundary of the detector?
Well, you don't have the Hamilton. Your boundary observables are not evolving unitarily just within the boundary algebra. You're not surprised if a particle arrives at your detector out of nowhere. That's new information. Whereas here, no new information can arrive at the boundary. You could predict at any time. I mean, the state in the boundary evolves unitarily by itself. In this collider, if a particle arrives at the detector, it's entangled with another particle that didn't get detected, then the state of the detector is in a mixed state, right, in the Schrodinger picture. Or the algebra of detector observables didn't evolve unitarily. Here, the algebra evolves unitarily. That's how it's different.
But you've only specified that the boundary observables evolve unitarily. If I have,
That's right.
if I have bulk observables, then
yeah, I'm
then
not
you
talking
don't
about
know.
bulk observables
But
right
but
now.
but in the thing that you're talking about, bulk observables would be important. I mean, if you only have access to whether boundary algebras at a single instant of time evolve unitarily, then you might think there's a paradox, but you also have to know how bulk observables are evolving from the point of view of the boundary.
I don't know what you're talking about. I mean, I'm just talking about the boundary algebra evolving unitarily and trying to understand how that's consistent with the fact that local quantum field theory in the bulk would say that things can be entangled with things in the bulk. Yeah.
Ted, so just to restate something that went by quickly in my talk, in order for this relation to be true, that d by dt of O is the commutator with the boundary Hamiltonian, you have to have this relation over here that basically you've constructed something that commutes with the constraints.
Mm-hmm.
And really in gravity, that's the same as basically solving for unitary evolution in the bulk.
In terms of
if that's a
internal
bulk
time.
operator.
Yeah.
Yeah. So you really only have this statement true, once you know the unitary bulk evolution. That it's only once you've done that you
That's
have
fine,
this statement.
but isn't the paradox, we're just trying to confront a matter of principle that's puzzling to us, so.
Well, okay, well, I'll let you.
Jonathan has been raising his hand for a very long time. I don't have a microphone. It doesn't matter. There's still more degrees of freedom in the bulk potentially than the bulk. You're not claiming by looking.
You might have to turn it on.
This is the one that doesn't work.
Oh, sorry about that.
You're not claiming that by looking at the boundary, I know what's going on in the bulk, because there could be much more degrees of freedom in the bulk. This is not ADS-CFT. There's a lot more degrees of freedom potentially in the bulk.
There's no assumption here that the boundary algebra includes all observables, although it might. But this statement is independent of whether or not it does.
So why isn't the evolution then still unit? If I look at the combined states, then isn't that still evolving unitary? I have a unitary operator which initially was just acting on the boundary. The boundary was just evolving unitarily, and now another particle comes in, and now it's acting on that, if I'm going to include that in the boundary, and I'm not sure I see that. And so the overall state is still pure if it was initially pure. Whereas if I have an entangled state, I only act a unitary on the, so now your state is entangled between the bulk and the boundary, and I have a unitary acting on the boundary, the overall state is still pure.
What do you mean by overall state?
The state of the bulk and boundary.
I'm not talking about that. I'm just talking about the boundary algebra that's evolving unitarily, despite the fact that things seem to come in interaction with it, which are entangled with other things. That's the paradox that needs to be resolved.
You're implicitly assuming the boundary algebra only corresponds to things that are near the boundary in the bulk.
No, I'm not assuming it. It is what it is. I defined it.
If the boundary algebra has an operator that can...
Well, exactly. That's where I'm going to get to explain it. But let me get to there so I have time to say interesting things.
The assumptions are highly non-trivial that you're making.
I'm not making... What assumption?
They're not supported in
Wait, what assumption?
That when you're somehow assuming that this neutron star there in the middle doesn't have a representation in the boundary algebra.
No, I'm not. I'm not assuming that at all.
But if you're not assuming that, why are you surprised that...
In fact, I'm going to conclude that it does. I'm going to include maybe not that everything does, but everything that needs to be represented in the boundary is represented in the boundary. I'm giving a different perspective on how we should think about holography. That was the topic I was supposed to talk about, holography and gravity. In a point of view that doesn't invoke the CFT, you don't have to feel affiliated to string theory. You're just using what we think we know about the principles of diffeomorphism invariant quantum gravity.
Can I ask a question before you go? I think I'm still confused about this setup. I'm sorry. Maybe I just misunderstood. It sounds like... Thank you. If I look at the picture, how is this question you're asking different from this question of precursors? Where you have
It's very, very similar. That's another example. And I was going to mention precursors.
Okay, because the solution, because the solution to that is essentially what Raphael was saying earlier, that there has to,
right.
This instant where if I think of this ray being emitted, if you believe bulk causality, you'd think it would take some time to get to the boundary. But if you believe ADS-CFT, there should be an exact representation along each time slice, and it has to just be some very non-local...
exactly. I totally agree.
You're going to clarify the difference later, I guess?
What difference?
Well, this is just this question. So this what you call the boundary information paradox, I don't see a paradox. It's just the issue of how...
Well, the question is how is the information about... The paradox is how can something be encoded so it looks like, as somebody was starting to push me into saying, I have a kind of Hilbert space that's a tensor product of a bulk piece and a boundary piece.
But I don't understand. These Hilbert spaces are
But,
dual.
but the
you
thing
can't-
I'm going to represent, the thing that's in the bulk that you're saying, and I agree with it, also has an avatar representing it in the boundary that looks like it's somehow violating some principle of quantum mechanics or some algebraic property of quantum mechanics, that I have a double copy of the same information in the state. And this is what I want to talk about, is how we resolve this paradox within quantum gravity.
But you're treating this
You
as a
may feel
unified
like you
Hilbert
already
space?
understand it,
That's-
then you're free to leave the room. I mean, I'm just going to explain how it should be understood in quantum gravity.
Maybe it'll become clear as you go on.
But can you clarify what, are you saying that there's a tensor, you have two Hilbert spaces, the boundary Hilbert?
I'm saying, no, I don't. I think this is the wrong picture. I'll explain why, and why the fact that it's wrong resolves the tension here.
Okay, so you don't have, so the boundary is not a different Hilbert space to the bulk. In which case, you're almost at ADS-CFT.
Well, I don't want to, and I don't need to commit yet to whether or not the boundary algebra includes all observables. In fact, I suspect strongly it doesn't, quite simply because if I happen to be talking about quantum gravity in a setting where there was no boundary, like a compact universe without boundary, I don't want to be pushed into the corner of saying that there are no observables in that theory. So I think there probably are observables that are detached from the boundary. But that's not relevant to the question I'm asking.
But just to clarify then the starting point, you have a Hilbert space which is the bulk. You have a Hilbert space.
No, I'm not saying that. I don't have that. I don't have that. I have the Hilbert space of states that are annihilated by the constraints. Maybe I had a kinematic Hilbert space that was just the whole bulk all the way out to infinity. But I'm considering, as Daniel was talking about, states that are annihilated by the constraints. So then the physical Hilbert space is some subspace of that kinematic Hilbert space. This is not useful, all this discussion. I won't get to be able to say anything new. You'll just be asking me questions, to address the question you want to ask instead of what I wanted to say.
But in particular, if you have a bulk particle, say. No, I think I'm going to, well, anyway. Then that corresponds to a dressed operator. So you have, as part of your complete Hilbert space, the operator that creates the particle and the dressing that goes out to the boundary. That's the kind of thing that satisfies the constraints.
That would be an example of an observable that satisfies the constraint. Okay, so you could object to this actually at an earlier stage than the ones that you are. And in fact, an eminent physicist who did strongly is Bob Wald. And I wanted to figure out how to address his objection. The objection was to just look at the classical limit of what I'm talking about and replace these brackets by Poisson brackets. And then everything I said already would still be true. And we would have concluded that maybe I should switch to this board. The front board comes down, back board goes up. Oops. This is a perfect, yeah. Oops. This is the front board. What? Do you have to nudge it? Amazing. This is a perfect time to have that problem because what I'm now going to talk about is analyticity. So the problem actually, or the issue is analyticity. There's a really important analyticity underlying the quantum gravity that doesn't underlie the classical theory, and that's the resolution of Bob's problem. So I would have taken the equation I d by dt of my classical operator is the Poisson bracket of the operator with the Hamiltonian, which is going to be just the boundary Hamiltonian because I'm talking about a gauge invariant classical observable. And then I would have said, I know how to solve an equation like that. That tells me that O at t is the exponential of the operator of taking the Poisson bracket with the Hamiltonian, acting on the observable at time 0. And that this would be the solution to that. And so the algebra of boundary observables classically would evolve into itself. But that's definitely not true. Okay, that's definitely not true, because if we take a classically asymptotically ADS spacetime and take some slice on it, and take it to be exactly Schwarzschild ADS, let's say, in this segment of the boundary, then we know that in the domain of dependence of that section, we'll get exactly the Schwarzschild ADS solution. And we could have initial data here which differed from that in some compact set, let's say like that. This is a picturesque way of showing, just making like a graph, plotting a function of initial data, which is completely zero inside that region. And yet, the information in this can clearly propagate to the boundary, so that there's no way that the analog of boundary unitarity, or the boundary algebra of observables, doesn't evolve into itself in this case, classically. And this seems kind of puzzling. What's wrong with the argument? It seems like we just showed that it does. And what's wrong with the argument is that this isn't really the solution. And the reason it isn't is this involves basically an infinite series in T, and that series doesn't converge because the function isn't actually an analytic function of time in the boundary. And we show this in this forthcoming paper with an explicit example with a scalar field moving to the right, and just show how the series fails to converge. So then we need to turn back to the quantum theory and say, what's different about quantum mechanics that makes it analytic in time when it's not analytic classically? There was a question or a comment?
Is it obvious that you will be able to solve the constraints with such a profile?
Yeah. I mean, oh, you mean with zero? Oh, I see what you're saying. Yeah, thank you for mentioning that. There's a famous result from recent years, although I'm not sure how recent, named Corvino's result. There are solutions to the Einstein equations that are exactly, this is what you're asking me, right? Exactly Schwarzschild ADS outside some region, but differ inside. So there are solutions to the initial value constraint equations that behave that way.
Corvino shown, right?
Corvino and Schoen. Yeah, Corvino did it first by himself. Maybe they extended it. I think Corvino was a graduate student of Schoen. So there's it's a really important distinction. So what is it that's different about quantum mechanics? And the difference is that instead of writing this, so this is classical, in quantum mechanics, I would have written that O of t is e to the I t Hamiltonian O0 e to the minus I t Hamiltonian. So, and if H is a self-adjoint operator, using the spectral decomposition of the operator, we can define this exponential as a perfectly well-defined bounded operator. We might want to restrict to bounded operators for the observables to make sure there's no funny business in multiplying these two operators together. I don't mind restricting to bounded operators. And so then I just have the product of three bounded operators. It's perfectly well defined. And it's like manifestly analytic if you get into the theory of bounded operators. But to make this more concrete, Fuchs and I wanted to just boil it down not to operators being analytic in a parameter, but functions being analytic in a parameter. So we said, let's look at the expectation values of all of these boundary observables and see if we can see explicitly that they're analytic functions of the time on the boundary. And we're able to do that. If we make a further restriction that's slight, which is to project the observables so that they don't contain any energy components higher than some cutoff energy. So let's consider energy projected observables. Let's see, that's over here. So let me define O lambda. Lambda is an energy cutoff to be a projection P lambda O P lambda, where P lambda is a theta function of the cutoff energy lambda minus the Hamiltonian. Since the Hamiltonian is in the boundary algebra, and this is just some function of that operator, P is in the boundary algebra, and so if O is, so is O lambda. So we're talking about a subalgebra of the boundary algebra that's energy projected observables. And then we can evaluate in any physical state the time, the expectation value as a function of time of some operator. And then by inserting complete sets of states, of energy eigenstates, we can express this as a double sum, e to the I omega m minus omega nt. Some matrix elements of this operator, mn, just the mn matrix element of it. This will be 0 if either m or n corresponds to an energy eigenvalue above the cutoff. And then just the overlap of this state on m and n. So psi m and psi. So you can see now this is just a sum of exponential functions of t. So as long as the range of omegas is bounded, just by standard theorems about analytic functions, this is just manifestly an analytic function of t. So we did need to cut off at the upper end if we wanted to invoke those standard theorems. So we have analytically evolving expectation values. Therefore, you can predict the value at any time from the value at any other infinitesimal time window by just evaluating the infinite number of time derivatives at one time, and that'll tell you the value at any other time. So this is analytic in T. And so key thing, again, just to emphasize, this is not the case in the classical theory. So there's something fundamentally different about the quantum theory that lets boundary unitarity be so powerful.
This is also not invariant under ADS isometries, right?
What's not invariant?
The statement that you project on energies below a certain energy, because you
Yeah,
can
I
always
pick one
do the
particular
equivalent of
generator.
boosting. Yeah.
I pick one particular time
So you're breaking the
translation.
symmetry, yeah.
You could pick a different one and still get an analyticity result.
So you said it's not the case classically. So did you only show that by counterexample, or is that even more general?
Showed it by counterexample. Yeah. So we showed it. There's the fact that the evolution can't be determined by this Corvino result, and then what we showed explicitly by counterexample wasn't in gravity. It was just to take a scalar field, massless scalar field in 1 + 1 dimensions, write down this infinite series, and just given the initial data for the scalar field, and just show explicitly that it doesn't converge to the physical solution to the differential equation. It's really surprising because it just seems like you're writing down obvious first order equations. You should be able to just iterate it. But if the initial data is not analytic, then the solution is not analytic.
So
Yeah.
you prove that there are some functions that are not analytic in T, but not that all functions are not analytic in T.
No, because I guess it depends on the O that you stick into it, right?
Here they all, any, oh, here?
No, I'm looking at the right, actually. So the right says that there's some, in the quantum theory, there are some observables that evolve analytically in time.
No, I'm saying all do. If all energy projected observables with any cutoff, any energy cutoff, no matter how high.
But that's not all observables, is it?
That's not all observables? Okay, yeah. Yeah, I don't know I couldn't make a claim about observables that are unbounded in energy, that have components that are non-zero at arbitrarily high energy. I don't know.
But how much of a contradiction we have with the classical case then? If
Oh, I see what you're saying, maybe. So you're saying the assumption of bounding in energy and the assumption of analyticity classically would be somehow the same?
I'm just asking whether there's a sharp distinction between what happens classically.
Okay, no, it's a good question.
And the fact that we have focused on a particular.
Well,
class of
certainly the
observables.
classical energy of this particular initial data set could be just finite. And I still have this situation. So yeah, there's a sharp contradiction. if the basis of comparison is energy spectrum of the quantum observable versus energy of the classical configuration. Let's see. I should be aware of time. Okay, I just want to truncate this to the essential. Okay, so Steve, is it okay if I take 10 more minutes to finish?
Yeah, there's been a fair amount of discussion during the talk.
Oh, okay.
So,
so the resolution to the paradox is, of course, what people have been saying, namely that there has to be like a copy or an avatar of whatever it was in the bulk that the asymptotic excitation was correlated to, has to be represented somehow in the boundary. And the only alternative resolution to that is that the Hamiltonian isn't really in the boundary algebra. I just wanted to make a quick comment about that. So it looks like it is in classical gravity, and in the quantization of GR per se, it's in the boundary algebra manifestly because it's the ADM Hamiltonian. But we know that theory is not UV complete. And so we'll have to start adding something to it. And if what we add is, let's say, for example, string theory, or if we complete it to string theory, the localization properties of string theory are not the same as those in general relativity. Maybe the Hamiltonian, the full Hamiltonian of a UV complete theory, actually couples things that can be localized at the boundary to things that just can't be localized. In which case, the claim that H del, if I wrote it anymore, is really localized in the boundary algebra may be wrong. But I think that actually that wouldn't get out of this paradox probably, because even if that's true, whatever those effects are, they're very small. And we're talking about sort of order unity problems of evolution, unitary evolution in the boundary algebra. So some tiny correction with a small coupling to some string degrees of freedom that are very suppressed because anyway I'm at low energy and I don't have enough energy to excite them shouldn't really change the story. So I think the only solution is the one people are mentioning that we sort of know completely, obviously, from the ADS-CFT viewpoint, which is that somehow the CFT, well, it's evolving unitarily. Maybe, you know, whatever degrees of freedom it needs to describe to purify the external, the asymptotic quanta, it has in them. So that sounds good, but it actually raises a problem also that should be addressed, which is the algebraic no-cloning theorem, which I want to now discuss. You can't just happily say, oh, there's a copy of this observable in the boundary and also in the bulk. It's as if, so let me describe this algebraic no-cloning theorem. It's actually like one of these one-line theorems. It's mentioned in passing in the paper by Almeri, Dong, and Harlow. The paper on the quantum error correcting code picture of holographic bulk reconstruction. They mentioned this result. And it's just the fact that suppose you have a Hilbert space, H phys, I'll call it physical, that's a subspace of a tensor product of two other Hilbert spaces. So I have in mind the case of general relativity where this is the constraint subspace picked out by the Wheeler-DeWitt equation and the spatial diffeomorphism constraints. Then the statement is that if, and suppose you have some algebra of operators on this space. So if an algebra A is measurable on both HA and HB separately. And by measurable, I mean you can find an operator that acts only on the HA factor, and it's the identity on HB, but it gives the same action on a state in HFIS as the original operator. So in other words, this means O on psi equals OA tensor identity B on psi, but it's also identity A tensor OB on psi. That's what it means to be measurable on both. Well, then obviously this algebra must be an abelian algebra, because any two elements of it, you could represent one of them by its action on the A factor, the other one by its action on the B factor, and because that means they have this structure and the identity commutes with everything, those two operators for their action on the state will have to commute. So if it's measurable on both, then A is abelian. Well, that's not good enough. We certainly are not interested in restricting attention to abelian algebras of observables on the boundary. The boundary algebra has more than that in it. And yet, so how can there possibly be an avatar at the boundary of some operator that could also be observable in the bulk? So that's another puzzle. So let's put that there. So how can O in A boundary also be, or how can O in the bulk also be represented in A boundary? And I think the answer to this is that we're only interested in physical observables, so they must commute with the constraints. So we need gauge invariant observables. The ones at the boundary, they're gauge invariant because the gauge doesn't act at the boundary. The one in the bulk isn't, unless we make sure that it is. And how do we make sure it is? We use what Steve is talking about, dressed observables. There are various ways you could construct a dressed observable. They're not the same. But whatever you do, Steve and Will Donnelly proved a dressing theorem perturbatively in quantum gravity, showing that all gauge invariant dressed observables with non-zero Poincare charges actually have to extend in their non-local structure all the way to the boundary. So you can't have a situation like where you have an observable localized here that also has an avatar over here, which would lead anyway to this contradiction, because if we had a non-abelian algebra of these, well, we would contradict the algebraic no-cloning theorem. But the dressed observable here has to actually go all the way to the boundary. So now, actually, the situation is different. There's no reason why this should commute with this, because this has support at the boundary also. So I think the resolution is that we shouldn't sloppily think about the black hole degrees of freedom or the resonance degrees of freedom or whatever that is in the bulk as being characterized by observables that can be isolated in the bulk. By necessity, in order to be diff invariant, they have to extend to the boundary. Actually, there may be ones that don't extend to the boundary, but those are not going to be the ones that we need to represent in the boundary in order for the boundary algebra to evolve unitarily. They may be just stuff that's isolated in the bulk doing its own thing. Yeah?
I mean, if you have an observable like that, would it in particular commute to the boundary?
No, in general not. It shouldn't.
So the one that is disconnected.
Oh, the disconnected ones. Yes, that would.
That will commute exactly.
Commute exactly, yeah. Yeah, then it would be like the Wheeler-DeWitt account of quantum cosmology, where you just have no time, you just have internal time notion of time evolution.
So at least in the context of ASCFD, we think there are no sides.
That's right, at least for the class of state, yeah. So I don't want to come down on that with an absolute definite opinion, but it does seem to be the case First of all, perturbatively, if we start with the vacuum of ADS and gradually build up, we can concretely actually represent what we think are all the effective field operators in the bulk as specific boundary operators. It may be at the non-perturbative level that somehow you get disconnected from that and more possibilities open up. But I just don't have a strong opinion either way, but it's not necessary to know for this account, I think.
But it will be totally decoupled,
It-
dynamically decoupled.
Yeah, it seems like it. Yeah. I think Wall and Merrill discussed this to some degree in terms of super selection sectors of the theory, yeah, which would be unobservable from the boundary. So I think that could be true.
Coming back to what you just said, at least perturbatively, if you're studying these, things like that would violate the dressing theorem, right? Any localized thing needs to be dressed.
Unless it had 0 Poincare charges,
Yeah, okay.
which it would in this case. I mean, that's part of the problem why we don't think most likely that it doesn't exist in the standard conception of ADS-CFT, because it would somehow be dual to a bunch of states that aren't carrying energy in the CFT.
Well, also zero.
On the other hand, the things Daniel talked about earlier today of like how you, if two CFTs can either be connected in the bulk or not connected in the bulk, depending on how you choose to describe it, then I feel on very thin ice in making strong statements about whether there could be observables that aren't represented with Poincare charges in the boundary. I just don't know.
But just a reminder, 0 Poincare charges means commutes with the translation generators, means translation invariant, so
Yeah.
completely non-local.
Yeah. Yeah.
Isn't there a tension between the Corvino-Shum theorem that you discussed earlier that says that there are excitations that are completely indistinguishable after some radius, and this dressing of operators here?
I don't see how to draw the contradiction yet, but maybe you could find one. I mean, in one case you're talking about a classical initial data set. In another case you're talking about construct a statement about all possible gauge invariant observables. You could, I guess, frame that classically. You probably have a dressing theorem classically also.
But also there's a quantum version of basically Corvino-Shum, which is constructing these dressings I was talking about, where they're very insensitive to what's going on inside. You could have a lot of different things inside, but the dressing only depends on the Poincare charge outside.
Mm-hmm.
I see.
Yeah, okay. So let me finish actually by addressing the one thing that Raphael thought was the only thing worth talking about, which is the Infahler paradox. So I understood the Infahler paradox finally because Raphael explained it to me patiently last summer. It seems to be based on, basically the lump of coal paradigm for a black hole. So you take the viewpoint that you have, you could have a pure state, you radiate a lump of coal that starts at 0 temperature, it heats up, it starts radiating. You understand everything about the quantum mechanics. The Hilbert space factorizes into the radiation degrees of freedom, the coal degrees of freedom, and then if you know the theory of the lump of coal and quantum electrodynamics perfectly, you, being Alice, could collect up after the coal has cooled down half of all of its entropy. Remember, it's in a pure state. Alice could distill out this special qubit that she knows will be perfectly entangled, or almost perfectly, with the next photon that the coal emits, let's say at a certain angle or in a certain spherical harmonic state. It has to be a very specific photon because her calculations, based on all of her measurements of all of these original photons with incredibly fine precision, told her the answer for which qubit would be entangled to a specific photon that comes out of the coal at a specific time in a specific state. So I don't contest that this sort of quantum information theory idea that would be possible somehow in principle. Now the issue though is to get a paradox out of that for the black hole, you have to imagine that the lump of coal paradigm and this protocol that Alice followed can be put into the black hole context. And we see and we know that it's not the case, because the Hilbert space doesn't factorize between lump of coal degrees of freedom and radiation field outside. And the measurements that Alice thought she was going to do to measure the quanta and also to know which photon coming out of the lump of coal her special qubit was going to be entangled with, how she identifies that becomes problematic in quantum gravity. We have to only talk about gauge invariant observables, or else we don't know what we're talking about. So it seems to me that the formulation of the Infahler paradox is illegal. It's not formulated within the theory we're trying to consider. And so I would say actually the burden is on Raphael to reformulate the Infahler paradox in a gauge invariant way, consistent with the principles of the theory we're interested in. And then if he still comes up with a paradox, we can try to solve it. But it's putting things out of order to create a paradox using a structure of the theory that doesn't really apply, and then ask you to use the theory, that is the general relativity, to resolve this paradox when the paradox may not even exist in the theory. So that's my take on the Infahler paradox, and what I meant by saying that the lessons we're learning, we will learn by carefully thinking through the boundary information paradox first, even though to most of you it seems like the answer is obvious, and only then come back and say, okay, now that we've understood that well, what should we think about this Infahler paradox? That's it.
Okay, more discussion.
At the risk of adding to the confusion, I've always been puzzled by the following maybe trivial problem. Due to Gauss's theorem, if you integrate over the flux on the surface, you get the exact value of the source inside. This particularly should hold for gravity. If I integrate over the gravitational flux on the surface, if I could do that with infinite precision, I would know exactly the energy inside. This means that if I would also know the Hamiltonian inside, I would just diagonalize that source that I found, and I have its eigenvalues, and so I have the Hamiltonian inside just by integrating the flux on the surface. Now, of course, this is not an experiment you can actually do because you need infinite precision, but as a matter of principle, what do you think of this?
I agree with it. I think this is, what I'm saying is kind of based on that fact. One thing I would comment, though, somebody said earlier before lunch that, I think Daniel said, by measuring with ultra precision the energy of your boundary state, therefore, you would be able to identify the state. I think that's missing something because you couldn't, that's true if you knew that it was an energy eigenstate to begin with, but if it's a superposition of energy eigenstates.
Even if my source is off diagonal, then also the integral I'm doing at the surface will be off diagonal.
But you have to measure all I want to say is you have to measure other observables to do quantum state tomography to really measure the full state. It's not enough to measure the Hamiltonian.
Maybe the word measurement is not quite good enough. You have a theory that tells you something about how to describe the gravitational field at the boundary.
Yeah.
In that theory, I take whatever the quantum state is of the total flux on the boundary, and I say the same, it will be the same as what sits inside.
Yeah, I think that's correct. I mean, modulo this issue about disconnected, like, internal degrees of freedom in the bulk that are not in any way registering at the boundary. But maybe those are geometrically not even in any sense in the same space-time, so I don't know. I just want to allow for the fact that I believe in quantum gravity without boundaries, that there exist non-trivial things to be said, like quantum cosmology, that there are observables that don't register at any boundary. So maybe they can coexist in a space-time that does have a boundary. But maybe, yeah. I keep wanting to make that caveat just because it seems possible to me.
Also, there's the small follow-up to that if you have degeneracies in the spectrum, then you won't see the difference between those as observed from the boundary.
Yeah, although Daniel made a comment about any degeneracy would be lifted because if you believe this fact that in quantum gravity there are no global symmetries. But anyway, I don't think that's important because in any case, I think you need to measure things besides the Hamiltonian to identify a generic state, right? So
You need, general correlators, say, if
yeah,
one correct.
so it doesn't matter if there are degeneracies.
But that's standard, right? You can never measure a quantum state. You have to have a very large number of copies of the state and then measure it over and over and over again.
Well, yeah, I mean, we're assuming standard quantum mechanics here.
So, basically you do quantum state holography.
Right.
Basis.
Right, but the fact that you need to do it many times is not, it's not just that you need to do it many times, but you also need to measure many observables, not just the Hamiltonian.
Yeah, that's true. But they could be simple, they could be observables that are very simple in the energy eigenbasis, like something that, like you do interference experiments on 2 levels, right?
Yeah.
In sequences of pairs.
Like off diagonal,
and that will tell you about
plus
that will tell you
MN.
the relative phases of the different.
Exactly.
So that will be horribly difficult in practice, but I guess.
Right.
But it's not infinitely difficult, right? Because it requires e to the s measurements that take e to the s years each. So, but it's not infinity, but it's, well.
So I can describe both, both the infollower, the Amps paradox, and this one in a relation. Like instead of using a boundary, I can instead look at an observer who's falling into the black hole, say, or who is sitting far away from the black hole. I can either. There's equivalent ways to deal with different morphism invariants, or not equivalent, but ways to deal with different morphism invariants. Either consider different morphisms which leave the boundary invariant, or I could instead consider different morphisms which leave an observer invariant, or I could consider all different morphisms and then just look at relational observables, these page-Reuters observables, between the observer and what she's measuring. So the state of the photon where Alice is a different morphism invariant observable, and I can use that to describe the Amps paradox, and I still have a paradox.
Well, I don't think so, because I think for Raphael to formulate the paradox, for Alice to possess the special qubit, I don't see any argument that she can do that using the kind of observables you're talking about. I only see the argument in standard flat space quantum field theory.
Well, I guess that for me the equivalent of your paradox would be, I have Alice, she has a clock. I want to consider the state of the thing she's measuring relative to her clock. And now if a photon hits her and interacts with her clock, it's no longer a good clock, and she might get confused into thinking that things are not unitary anymore if she uses that clock. In other words, a simpler resolution to this paradox is just to say there's a bulk system, there's this photon system with a different Hilbert space, there's the boundary system with a different Hilbert space. The evolution is just unitary on the boundary, and when the photon comes there, I act that unitary on that photon as well, and that's still a pure state after that. If I act a unitary on half of an entangled state, the total state between those 3 Hilbert spaces is still pure. So why isn't that just as good a resolution to the paradox? Just assume just assume they're all separate Hilbert spaces, and a unitary is acting first on the boundary.
Well, if they were, then we'd be able to run the Infaller paradox argument. And we know they're not because the principles of quantum gravity tell us we should project to the physical subspace of the tensor product you're talking about. So it's not the right Hilbert space. And anyway, if it were, then Raphael would run his argument and we'd have the Infaller paradox.
So can I comment on that? First, thanks for summarizing the paradox. And there's just one little detail that I think was not correct in the summary, which is that Alice would not be able to figure out how to extract the purification of some given outgoing particle just from the Hawking radiation or from the Cole radiation that has already come out at that point. She has to actually know what the full out state is. But there's no reason why she wouldn't. She might be in possession of the S matrix.
What's the difference between the radiation that came out and the full out state?
Because the thing hasn't fully evaporated yet, whether it's a black hole or coal. If you want to jump into the black hole, it had better not fully evaporated yet.
Oh, so she has to be able to predict forward what the final state will be.
She has to know what the final state is going to be. which is no problem. She might have an S matrix for that, or she might have measured it by doing some previous experiments with the same
I
instate.
didn't realize she needed to.
She needed
that
it's extremely subtle to get that particular bit out, and you need to know the full state for that.
Right. So, but I should mention, since you reminded me of that subtlety, that the Harlow-Hayden analysis of the difficulty of her job
That's closely related to this.
showed
fact.
that it would take like e to the s time at least to do the measurement. But I'm more concerned not with the time, because we have all the time in the world, right? It's really what is
well,
that?
you have to be able to do it
What
before
does
the
that
black hole's
incredible
gone.
sensitivity imply about the mistakes we're making in our analysis? We're making a huge mistake. We're using non-gauge invariant observables and a factorized Hilbert space to describe the thing in the first place, which we know doesn't apply.
May I comment on that now?
Yes.
So, first of all, I want to stress that the AMS paradox, or my formulation of it, is not stated in the context of ADS-CFT or, in fact, of any particular quantum gravity theory. It's stated in terms of the mutual incompatibility of certain things that we would like to emerge in the semi-classical limit from that theory. And it doesn't actually assume anything particular about the structure of the theory. So how's that compatible with what you just found? So I think the problem is the following. Would you agree that I can measure a particular wave packet in this room of whatever, the electromagnetic field? I don't need to go to some boundary that doesn't even exist in our universe.
No, I mean, you're using the accident that we happen to be sitting in a room that has a history, and so it's a very state-dependent thing. You're not describing an observable.
Let me maybe finish my argument, and then you respond to me. So I would assert, and you can contradict me later,
You asked me if I agreed.
that here at CERN we measure the states of particles that hit detectors. I don't understand what the history of anything has to do with that. Those are operators, and we can measure them. And we measure them despite the fact there is gravity in our universe. So they must be somehow approximate semi-classical observables that we can make sense of in a GH bar expansion.
Mm-hmm.
Right? And that's the answer in the particular case where we understand the quantum gravity theory. We can still measure some outgoing Hawking particle near the horizon of a black hole in that sense. It's just that the fundamental, ultimately non-perturbably correct definition of what we're doing can be given in the boundary. It contains small corrections. But small corrections aren't going to get you out of this contradiction, because it's at order one.
Here's why. I understood this from you, and I hadn't appreciated it before, actually. You're absolutely right. I agree that if Alice possesses the special qubit, then there's no escape. The subtleties of quantum gravity can't save us at that point, because she's just making measurements like they do at CERN in a frame, in a region near a black hole that's macroscopic at low energies. There's just no way out of the contradiction. If she knows she's got in her hand the qubit that has to be entangled with this Hawking quantum that's coming out. Where I think the argument fails is that she can't know she has that. Your argument, or the argument that would have said she could have possessed that qubit, is formulated in the wrong theory. And really, it's the burden is on you to formulate it. That's where the subtleties of gauge invariance,
but then you're denying the validity of quantum field theory on a curved background completely, even as an approximation.
No.
Which means that the way you're getting out of the AMS paradox is by violating the assumption of effective field theory.
No, that's exactly what's wrong.
If effective field theory is valid, you can do this.
You said yourself a moment ago that you agree with Harlow-Hayden that it takes e to the s time for her to do her job. That's not effective field theory at CERN. CERN has only existed for a few years. You're basically pushing the limits of a theory to the point where you have to keep track of e to the minus s corrections. And at that point, the things in the quantum gravity theory do make a difference. And therefore, you're not correct in saying that you've only used effective field theory where we know that we should trust it.
So if Harlow-Hayden was the essential argument here, then that's the one that you should have reviewed. I mean, that argument has been discussed extensively, and the pros and cons of, and
that's
I think
not the only weakness, though.
Well, but that's an important point. So first of all, if it really took e to the s time, the black hole in asymptotically flat space would be long gone by then. In ADS, the black hole sticks around, so you don't really care how long it takes. But by linearity and unitarity, you could have just prepared the black hole in a state where a particular Hawking particle comes out pure, and then you're done. The paradox is already over. So I don't think that Harlow-Hayden really is going to help you with this. But if we're going to go there, then that's the topic we should be discussing.
Well, it's not just Harlow-Hayden. I'm also concerned that how does Alice identify that particular Hawking quantum that her special qubit is perfectly entangled with. You can do it on a flat space background and just predict, but now she can only measure gauge invariant observables. So
she's measuring in a low curvature background a bunch of radiation.
No, but she had to know what observable
That's what
to
we do
measure.
here.
She has to know where she is and at what time and how to measure it.
How do we know that here?
Precision.
We make a bunch of
We're not
mess
trying to do it with that much
Atlas
precision.
and it comes out.
It's because we're not trying to do it at that level of precision.
No, I don't think so.
That we have to take quantum gravity effects into account.
Well, then you have to tell me exactly why semi-classical gravity breaks down, the perturbative expansion breaks down. Like, you have to say exactly where it is that I introduce noise into the problem that I cannot get around. Because this is, obviously something that people have searched for. I mean, it's not like, it'd be great if there was some operational obstruction to performing these measurements.
Well, I would say,
then we could say that's where it must be.
So I didn't pull out of this part of the argument, but I would say this now. So another feature of your argument that Alice could do this was that the Hawking radiation by itself should be self-purifying. Like when it all comes out finally in the end, the state of all the Hawking radiation is pure. But in this boundary information paradox story, I was arguing that, and you agreed, everybody seemed to think it was obvious, that in the boundary we already have at every time some other observable that's perfectly correlated with the Hawking radiation that's coming out. But that means that the assumption that you were making in giving Alice her instructions of how to distill this qubit were incorrect. Because they were based on a factorized Hilbert space where all of the quantum coherence was encoded just in this Hawking radiation, not in these global degrees of freedom of the gravitational field.
Right? So in ADS, I mean, we don't have to be in ADS. If I cannot observe the Hawking radiation, say in asymptotically flat space, at all, for some fundamental reason, because, I don't know, it's not sufficiently precisely defined as an operator, then why are we arguing about whether information is preserved? We should say that it's lost. If I can't even in principle observe it.
No, you can observe it. I'm just saying it's entangled with other degrees of freedom, which is the ones that we agreed are in the conformal field theory that are non-local distributed.
In asymptotically flat space, where are they?
Oh, wait. I stick to a case where it's easier to talk about it and not.
Well, in ADS, they're the same thing.
Let's talk about it in ADS.
These operators are the same thing. When the radiation gets to the boundary, you can think of each radiation wave packet or whatever as a local operator in the boundary. You can suck the radiation out.
Yeah, but Alice is not hanging out at the boundary just doing all these measurements. You were describing her as having.
Well, pick your frame. If you want to be at the boundary, the information comes out. If you want to be near the boundary, the bulk, it also comes out.
Everything non-locally distributed over the entire boundary to get the information that you want her to have. Yeah, I think the burden is on you to formulate your paradox in a diffeomorphism invariant way, and then I'll solve it for you. No, just joking. But seriously, I think if it's such a subtle effect she needs to do, you need to formulate it in a way consistent with the theory that we're in.
Okay, other comments or questions or objections?
No?
Jonathan, did you?
Well, I guess it's. I mean, I feel like you and Raphael.
Where's the mic? I don't know. Do we have a mic?
There's one here, but this is the one that doesn't work, right?
It now works. I think so.
We know that physics is translation invariant. We don't take our operators and make them translation invariant because we know we can do it anyway. So I mean, if we wanted to make any operator in quantum mechanics or in quantum field theory translation invariant, we would take it and then integrate it over all space, over all translations, group average it. And we don't bother doing that because we just say, okay, I'm doing that measurement here where I am. And I think that's the same. That's the same thing with Alice, who's measuring things, who's measuring the radiation. We could, if we wanted to, make it diffeomorphism invariant, but there's no need to because she's measuring where she is. That's the special place, and I just don't. I think there's just too much. I think there's too much emphasis placed on this mysteriousness of diffeomorphism invariance. Of course, it's incredibly important, but it's not going to erase problems where you can just as well describe them in a particular coordinate system.
Yeah, I guess I just totally disagree. I think the only paradox arises because of diff invariance, and therefore we have to pay close attention to the implications of diff invariance to solve the paradox.
A related comment is translation invariance, or translations are not gauge transformations. But anything that is not gauge invariant is not physical in a gauge theory.
I understand, but the same principle applies. I can still write something down which is not diffeomorphism invariant, and then group average it to make it into an operator, which is, as long as I have as long as I include my measuring device in that description.
Well, yeah,
I mean,
there's a question
these
of
are
how to construct the appropriate diff invariant things. In fact, we're going to have more discussion on that tomorrow. So, but you do need to construct diff invariant things in the end to describe physical.
But they've been well done. These kind of evolving constants of motion and all these things that people have constructed such things, and you can go in one picture or another. And I guess I would agree with Raphael that you're almost denying that we can make measurements near black holes that we would in flat space.
So evolving constants of motion are also different variants.
That's right. Well, that's what I'm saying. You effectively take. You include your clock into the picture and make it into an evolving constant of motion, and now that observable is diff invariant.
Yeah, but that's already after whatever.
That's right. So you take an observation which refers to a coordinate system, and then you group average it with the observer in the picture to make it diff invariant, and it corresponds to the exact same thing.
But I guess the important thing is that this coordinate is a dynamical variable, actually. So, and that's a bit different. You can't confuse it with the coordinates in some classical space-time background that are not dynamical.
Well, in classical general relativity, you also have to be. I can also only consider diffeomorphism invariant.
Sure.
Observable. So it's the same. There's no difference. It's not that. The classical theory is not so different from the quantum theory in that respect.
Well, you can do it classically as well, relationally, but then that's not a description in terms of space-time coordinates necessarily. You just relate your dynamical variables relative to some whatever scalar field or so that's parametrizing.
Exactly, to the observer, to Alice who's there.
But it's not a gauge fixing or something like this, because I think that's what you said.
No,
But in any case, I will speak a bit more about this tomorrow.
Okay. Any other comments or questions? We're worn out? Okay. Well, let's thank Ted again and then break.